Okay, guys, come on. Take a seat. Last hour. Andreas can do it, you can do it. New topics. Okay. Yes. What is the saturation point? Yes. Saturation point. So much, I'm sorry anymore. Okay, can I say to anybody who's taking photographs, if you have photographs to share, can you give them to Paul, and we'll have a projector during dinner, and we will have these photographs running in that, and we can put them on Facebook and so on. If there are ones you don't want to put on Facebook, I'm not sure. Yeah, give those to Sean. We'll get them. Are you asking because you're worried about that, or are you asking because you want to see it? Paul's going to organize that. Okay. Yeah, so do we have a Facebook page that they can sign up for? Yeah, so we have a Facebook page which you can sign up for, and then you'll be able to see those photographs, okay? And so on. And other things. So, Andreas, over to you.
Okay, so
take us through.
Last topic. A different topic for a change. But so we're going to be talking about photothermal coherence tomography, and that is also relevant to people who do optical coherence tomography, because this is the equivalent, the photothermal equivalent to that. But before going into this, I would say, well, why do I want, let me put my next slide here, why do I want to do photothermal? Well, in photoacoustics is a propagating field. The wave equation that you have is a second order in time, which means like you can have a propagating pulse. Pulse goes forward, it goes back, and so on. You have a time delay. Heat conduction is different. Heat conduction is a diffusion field, and it is very different to the optical diffusion that Boas presented yesterday. That is, both of them have similarities. Once I have diffusion, then I have propagation. You have lossy waves, I have loss in energy, and I propagate in waves that I cannot turn back and have a recurrence of the original operation. That is, I cannot reverse time. You know that when you take a course in mathematical physics, where because it's a second order derivative in the wave equation, if you change the plus t to minus t, you still get the same wave equation. But if you change the plus t to minus t in the conduction heat transfer, you get a different equation. That means it's not reversible. Heat transfer is not reversible. Same thing in many ways happens with optical fields, except there, in order to be able to see the dynamics, you have to have enough, you have to be working with hundreds of gigahertz or so in order to be able to see the light propagation. But light and heat basically obey very similar equations. So the important thing about heat is that ultimately it is a component that is missing from photoacoustics. What is not converted into acoustic energy is converted into heat. There are other conversion channels. One of them is just by going light into light. So you can get, transfer, optical transfer to optical transfer. So you always have, when it comes down to photothermal detection, you have an efficiency. That is a non-radiative quantum efficiency. How much of the light is converted into heat? If 100% is converted to heat, your efficiency coefficient eta is equal to 1. If less than that, then you get less and less. So if you have a mirror and you try to produce a thermal signal, if 99.9% of the light is reflected off the mirror, then your non-radiative quantum efficiency is 0.01. That means very, very little heat is going to be produced. So, but on the other hand, as long as I have an absorber, which is tissue, the same thing happens just like it happens with acoustics. That is, you have an absorption, but now you don't have a thermoelastic effect. You only have the thermal energy conversion. So you've just gone from optical to thermal energy. But what was originally absorbed optically, it carries a signature in the thermal field. However, this is a diffusive field, so the methodologies are different, the parameters are different. However, if I can start using heat as the photothermal phenomenon as an imaging effect, and I can do that with some classes of materials, that is very important because we have the technology already. I don't have to have transducer arrays. I don't have to have phased arrays. I have infrared cameras. They exist already. I don't have to put the sample in water because of impedance mismatch. I can propagate radiative heat transfer in the air. So if I can do that, the technology already that could produce imaging is there. It's just a question of how do I do it? And how do I do it to beat the diffusion? So part of what I'm going to present is, first of all, how does photothermal detection work, which is modulated detection, kind of pulse photothermal, but have been using modulated for the same reasons I'm using for acoustics, because you can actually get those very high sort of against background signals. So have been using these for things like controlling the depth, because now if you have a frequency, that's the other concept here, because photothermally, just like for acoustics, is a low-pass filter. For the thermal signal is even worse so a low-pass filter. That is, you have a very strong exponential decay into the sample. So if you modulate at a single frequency, what you're doing is you get information across the entire thickness. Single frequency means you have a certain diffusion length. This is it. Your heat is penetrating down to a certain depth, which is given as a square root of the thermal diffusivity of the material divided by the modulation frequency. So the higher the modulation frequency, the closer you look to the surface, because heat has not had enough time to propagate deeper. And of course, the higher the diffusivity, which is the rate at which heat is moving into the sample, the deeper you can see. So you can see why it is proportional to the alpha and inversely proportional to the F. And the square roots, well, the square roots are there because it's a diffusion field in its first order in time. So every time anybody deals with heat conduction, they're going to be seeing all sorts of square roots going everywhere. So that's the characteristic of that. So what you have is an absorption event, exactly the same as for acoustics. You have periodic heat generation. This is the frequency at which you're modulating your light. You have now instantaneous. You have essentially two different modes. You may have three, but you have two different modes in photothermal imaging. One of them is going to be radiative heat transfer, and the other one is going to be conductive heat transfer. So radiative heat transfer is Planck emission. You have a black body or a gray body, the temperature rises, suddenly you see light out there, infrared light. The sun is a black body. Okay, we have infrared cameras, infrared detectors are there because your body is an infrared emitter. So at night I cannot see the visible light, but I can have infrared goggles, I can have a camera, and I can see the heat out of your body. And if you can, that's infrared, and in this planet, our eyes are not made to see the infrared. But if you're the predator, and you come from a different planet, your eyes are made to look into the infrared, because that's what the predator. So remember Arnold Schwarzenegger, what did he do when the predator was sort of trying to catch him? He got out of the water and he kind of basted himself in mud. And the reason he did that is because mud would actually prevent the infrared radiation coming out of his body, and without the infrared radiation, even if you'd be standing in front of the predator, of the monster would not see him, because his eyes are there for the infrared detection, not for visible detection. So the heat of the body you could do away with just by putting mud all over you. That's what he did, and he got away, and there was a movie actually made out of him. So the thing about this is, once I have radiative heat transfer, and this is essentially, this is simultaneous with the heating source, because photons have essentially infinite speed, and then there's conductive heat transfer, and the speed of conduction is slow, much slower than the speed of sound, of course much slower than the speed of light. So anyway, what we have is, if I have the instantaneous Planck emission, then I only get an amplitude change, because there's no phase shift. But if I also have conduction, then there's going to be both amplitude and phase, because heat takes some time to come out. So I end up with something that's called thermal waves, And depending on the absorption coefficient, one of the parameters is the absorption coefficient. Absorption coefficient is higher, the thermal signal is going to be higher. So I can do spectroscopy, very much like with photoacoustics. So I can have higher amplitude and less delay time. And the reason for that is because the optical absorption coefficient is distribution is very close to the surface, so the optical and therefore the thermal centroid is very close to the surface, and that means a little shift from the surface. If on the other hand the absorption coefficient is very low, then I get heating all the way to the body of the sample. The central mass of the heat of the thermal wave field is somewhere down there, so it takes more time to come out, so the phase shift is longer. So phase and amplitude are there. Now, what you have is, there are challenges though. If you were to use this as an imaging modality, then you have a challenge with the spatial localization of thermal waves. There's essentially little localization. Heat, once it goes, it doesn't wait for you, it doesn't stay there. So as a result, we have things like, diffusive things that look diffuse. I say, oh, this is not sharp, it's diffuse. When you say the word diffuse, that's exactly what you mean. I don't see sharp boundaries, I see some things there, but because heat propagates. You don't want to be, for acoustics, you don't want to be in the diffuse limit because your image is going to look unsharp. Whereas you want to be fast enough so that heat does not have time to be conducted out. Here, you're facing that if all you're looking at is heat. So you have cases like, well, the heat diffusion equation, which is the Fickian field, that says it is second order in space because of diffusion and first order in time. But on the other hand, when you look at this, the heat, when you write the heat equation, there's an approximation there. So the approximation is that the speed of the thermal field is infinite. So there is no wavefront there. There are no wavefronts because it's infinite. That's at least mathematically infinite. So you do not really have wavefronts. You cannot do wavefront profiling with those, but you have a diffuse transport, and at the same time you have poor diffusive axial resolution. So this is what you're fighting against if you're trying to do imaging that way. So this is one of the examples that we put down, that is an absorber that's a certain steps down from the surface of the sample and goes deeper and deeper and deeper, and then you see how much of this wiggle, as you have an absorber go from here to there, and eventually you see kind of peters out and you lose your spatial resolution as a function of depth. So this is what but nonetheless, if you can do this, then you can have a very nice thermophotonic imaging, and of course, multi-frequency introduced again these radar methodologies into the thermal wave field. So just like I had a chirp for acoustics, I also generated the thermal wave radar. So I introduce a linear frequency modulation, and then I can also introduce binary phase-coded modulations, pretty much like what you do for acoustics. The difference being, though, that in this case, the frequencies are between maybe sub-hertz to maybe 100 hertz, or maybe 1,000 hertz at most. So you're not going to the megahertz range. That is not, because heat propagates little. So you cannot reach those deep depths that you reach for acoustics. So this field is not going to be very good in trying to get information down from 3 centimeters below the surface, but things that are close to the surface, it's great for, and also in areas or in applications where there is so much scattering of both the optical and maybe the acoustic component, such as in things like hard tissues, in which case photothermics competes quite efficiently with photoacoustics. So, but again, as I said before, match filter and cross correlation, it's the same thing. We get a peak, like we did with photoacoustics. And you also have a phase shift, so both of these amplitude and phase are here. The match filtering compresses the coded waveform into a narrow localized peak, and narrow is relative because you always have a loss. So it's a lossy peak. You can never get really narrow, and that's basically one of the things that you're fighting against. So what I'm showing you now is how we ended up eventually with this concept of thermal coherence tomography by trying to fight against the loss of thermal energy that's germane to the photothermal field. So to just get started with this, you have the thermal diffusion length. It goes like 1 over the modulation frequency. So higher frequencies, shorter length. So if you use a methodology, which some of you are familiar with because I saw a couple of posters, photothermal radiometry, that is actually a method where you're picking up the Planck emission, the black body emission from the solid, from the sample. You have a detector, an infrared detector, and you can use that dynamically by modulating the heat just because you modulated the light. So you have an excitation waveform, which could be a single wave. If it is a single sinusoid, it has two spikes as a Fourier transform, and the response is going to be at exactly the same frequency, but of course it's going to be a different amplitude. It's going to have a phase shift associated with it. But if you put for the thermal wave radar, you put a chirp in there, so this is the input, the Fourier transform of this chirp, and then this is the response of the sample. So you see it's very heavily weighed at low frequencies and very little weighted at the high frequencies. This is the thermal damping effect. But by having the thermal damping, this is actually, it can be considered to be a problem, but it's not a problem, it's actually an advantage, because you can do depth profilometry. It allows you to do depth profilometry even if you have a single frequency at a time, because high frequencies give you information near the surface, and then you can go with lower and lower frequency, and you get deeper and deeper and deeper. So with some inversion algorithm, you can have to solve the inverse thermal diffusion problem, thermal wave diffusion problem, then you can invert the signal. So from amplitude and phase, you can get information like thermal diffusivity or thermal conductivity as a function of depth. So this has been done. We have done a fair bit of that ourselves and other people as well. So anyway, this is the basis for that. It's just instead of having a wave equation, you have a diffusion equation, and then you also use match filtering, as I said before, for acoustics, so that I can get a high signal to noise ratio with a thermal wave radar. So again, the match filtering, the same thing as we did with the for acoustics, and we get a high signal to noise ratio, and this is the delay time now. The delay time in the thermal field, it does not depend on anything like the speed of sound or anything like this, but it depends on the thermal diffusivity. So the thermal diffusivity, the delay time would be something like the square of the distance from which the signal is coming divided by the thermal diffusivity of the material. And thermal diffusivity is a dynamic parameter. When you have a cup of coffee in your hand, you just have a cold cup of coffee, a cold cup, and then you put hot coffee in there, how long it's going to take before you feel the heat depends on the thermal diffusivity of that medium. The higher the thermal diffusivity, the earlier you're going to feel the heat in your hand. On the other hand, so this is dynamic, because heat propagates. On the other hand, thermal conductivity is a static parameter. That is, usually I have a wall here, I have a window, there is a temperature T1 here, a temperature T2 there, and then there is a temperature gradient. So your windows have to have low thermal conductivity, right? If your windows are made out of copper, you're in bad shape, because the cold weather out there is going to be transmitting itself immediately. The temperature is going to be low inside your apartment, which you don't want. You want to use glass, because glass has a very low thermal conductivity, so the temperature gradient between the front and the back is going to be really large. Very low temperatures here, high temperatures there, because you're heating the apartment. So conductivity is a DC, is a continuous property. Diffusivity is a dynamic property. And diffusivity depends on the ratio of conductivity divided by the density times the specific heat. So it's proportional to the conductivity, but density is also involved in there. So the delay time then depends on the diffusivity and thickness. And these are two parameters that you can measure. This has been used a lot in non-destructive testing as well, because that's what you want to do. A lot of times this is very useful. Having a material has a defect below the surface, that interrupts the flow of heat, and you can see the defect as a function of a change, amplitude, and phase. I'll show you a couple of these things.
For your typical measurement, say non-destructive testing, what's the frequency span of that modulation, and how long is it? Typically?
I'd say typically from 0.1 hertz to 10 to 20 hertz.
Okay.
That would be the range.
And how long would it be on?
So that would continue, right? So you could have it on for a few milliseconds, and then...
No, I'm just saying, so it's typically a few milliseconds, yeah. That kind of
you can repeat a few, of course, the more you repeat, the higher your signal's noise ratio is going to be. So this is where you have a cross-correlation function, so we know that by the time we end up with your cross-correlation function is the inverse Fourier transform of a product. So this one here is the transfer function of your system, and this one here is the physics of the photothermal signal that has been generated. So a very typical Fourier transform analysis. One of the things that we know is you can measure sample thicknesses. So you look at this delay time versus thickness. So what I'm finding is that as thickness increases, the delay time decreases. What is the delay time in cross correlation? It is where the signal is coming from. So I have a delayed time, so this is a semi-infinite medium. I have a delayed version of the input waveform, and it correlates with what comes out to me. So when I heat the surface, let's say an opaque material, such as a piece of metal, when I heat the surface, then the thermal centroid is somewhere below the surface within the time of the excitation. So when it cross-correlates with the delayed version of the incident waveform, which is what this one is doing, it gives you a peak at a certain time. But the rest of it gets lost into the sample. The heat propagates in a semi-infinite sample. If the sample is not semi-infinite and it has a certain thickness, that's 100 microns, then what happens is the back surface is acting as an impedance. So it prevents the heat from going to the bulk. Well, you can actually model this as another source. It's another thermal source back there, because the heat is not going anywhere, it's accumulating. So then you're also picking up information from that back surface. So you have heat going forward. In some ways, you have accumulated heat. Some people call that reflection. It's not a reflection, it is not a transmission, it's accumulation and depletion. This is a thermal field we're talking about. It's not acoustics. People have made those confusions for certain decades, but nonetheless, because there's heat coming to you and it's coming in at a later time, then the peak shifts to a longer time. So you can see that if I have a certain thickness, the thinner the thickness, so the longer the time, because I get information from the back surface. And then as the thickness increases, the time decreases more and more. Eventually, it becomes independent of the thickness, because it's just too far, too deep for me to see anything coming back to me. So that means that I can actually measure, do some thickness measurements if I know the thermal diffusivity is called thermal property. It's also called thermophysical property. So the whole field of thermophysics is involved in this. Very similar to what we've done before. That is your thermal wave field. Here's a signal generation drawing. I have a CW laser. I modulate that with a chirp. And then I take the light, I focus it on the sample temperature rises, it could be focused, it could be defocused, you could have 1D, 2D, 3D, you name it. All of these things depend on the size of the beam versus the size of the diffusion length. If the beam is large compared to the thermal diffusion length, then you're going to be 1D. If the beam is very small, so you can get like a cylindrical kind of isotherm, different isotherms, so it looks like a half sphere that moves away from the point of thermal generation. So in that case, you have lateral degrees of freedom too. So it's a 3D. So I can have two channels in phase and quadrature, again, through a Hilbert transform. This is memories of what I said 2.5 hours ago, and I can get mixing of these two and a weighting function to get rid of some of the side lobes, even though here side lobes are much less important than acoustics because they're already dampened. So you have very little sort of interference from side lobes, but then finally you do this mixing and low pass filtering. So what I'm describing here is a lock-in amplifier, because the lock-in amplifier does exactly that. It mixes the signals, it picks up the signal component that corresponds exactly to the frequency of the excitation. So it's a mixer and a low pass filter. And it gives you information out of the DC. It sends everything to DC. So even though you put an AC there, you have two DC signals, an amplitude and a phase coming out of a lock-in amplifier. And you can do that also for the entire chirp, because the lock-in fixes one frequency at a time. But this gives you all of the frequencies, demodulation, modulation first, and then demodulation, amplitude, and phase. So here I have the output, amplitude and phase. You can do the same thing with the single frequency, and this is a thermal wave radar, once again, with the multi-frequencies. Instead of having a single lock-in, it's as if you had, 100 lock-ins, each one of them monitoring one single frequency, but they're going all at once. So I have the reference signal, FFT of the reference signal, so that I can multiply instead of integrating, because remember the Fourier transform of a signal in time, which is actually going to be a convolution, an integral, is going to be a product. So products are easier to work with and faster. And then you also put your filter, which is the complex conjugate of your incident waveform that has been translated by a certain delay time. All of these to give you a high signal to noise ratio, F omega star, complex conjugate, and then you get the signal out of the mercury cadmium telluride detector. Mercury cadmium telluride detector started out long, long years ago. Primarily they were essentially DC, but then they started going into the AC mode. You can get megahertz infrared detectors right now. They're very fast. They are very much centered in spectral ranges, so depending on the spectral range that you want, you can get a parameter that's called detectivity. And the detectivity usually is quite high if the spectral bandwidth is small. If you spread the spectral bandwidth of the infrared detector, the detectivity is low. So in many cases, you have to decide what spectral region in the infrared you want to monitor. You want to monitor, is this going to be a spectroscopic measurement? Is it going to be a measurement of a material that's opaque? So spectroscopy doesn't matter. All that matters is the black body source, the black body curve. And then you really look at the peak of the black body is about 7 or 8 microns for room temperature, but then you shift to shorter wavelengths as the temperature rises, and eventually you wind up with the visible and UV with the sun, which is 6,000 to 7,000 degrees. So obviously the black body moves into the visible, and then these infrared detectors have to be, most of the time you don't have to custom make them, but it's good to know what spectral response you're looking for. So that takes the signal and puts it into the correlator, and you get the response out. You get an amplitude and a phase out of this. So the first thing I'm going to show you is, as I said, this whole thing started just from non-destructive testing. I know that there are no non-destructive engineers here, but nonetheless, you started looking at holes that are made below the surface of a piece of steel at different depths. So this is the deepest hole, 3,000 microns, 3 millimeters. 3 millimeters is very deep for thermal conduction. So you want to know how good your methods are by being able to monitor that deep hole. And this is pretty much the most challenging of all samples because there's no light propagating anywhere. The light just sits on the surface. All you see is the heat, is the thermal component in there. So you don't have the light to help you. With tissue is different because light propagates in the tissue. So I can do better with tissue. But this one here is the most stringent kind of measurement that allows you to see how good your methodologies are. So if you do, let's say you stick around to a photothermal measurement with using photothermal radiometry that I showed before, that is single frequency at a time, and you have a pretty good idea what frequencies you want to use, because the frequency has to be low enough to be able to reach the defect below. But it also has to be high enough so that there's enough of a signal coming out to the surface for the rest of the sample, for the rest of the holes. Because if it is too high, then you're going to miss some of that. If it is too low, then you're going to miss the entire thing because the resolution is really low. So it has to be somewhere in between. But here are anyway 3 of those holes, and then the other 3. So you see the 3 narrowest, shallowest holes are okay. You barely see anything like that. But then if you start using the radar principles, and suddenly out of 3, you see 3 of them standing up really proud and high, and then the other 2 are also showing up, and you kind of see this one here. So the thermal wave radar is definitely an improvement over the single frequency measurement. And these are the kinds of things that you see. These are the holes in terms in increasing depth, and that you see these 5, and you maybe you don't see the age 6. But then you can also use the imaging. You can do imaging exactly the same way that we mentioned before, the real part and the imaginary part, so it can get an amplitude and a phase based on the radar principles. How do you do that physically? You have an infrared camera. One of our first approaches is in dentistry, because dental fields are, the dental samples are just right. You have, your teeth has enamel that's quite thin, and then there is a dentin, and then you go to the pulp. So these distances of the order of a few hundred microns to a millimeter or so are just right for thermal wave fields. So that means that one of the first applications is in dentistry. In fact, we have made this application. Now we have a company that sells dental detectors. But for the camera, we don't have that yet. It's just single point measurements. Now the camera looks at the sample here with a mid-infrared camera. This is a CITIP titanium. This was made in France quite a few years ago. Now these cameras have been taken over by FLIR. FLIR is very important around the world. It's a big company and it sells a great majority of infrared cameras. These cameras are not very cheap, by the way. I mean, the best quality cameras would set you back by about $60,000. They're not really cheap. But ultimately, you don't have to have the highest quality of image, depending on what you do. There are some cameras that cost $5,000. Maybe those cameras with the right signal processing, you will be able to address your imaging needs. So anyway, what happens is, it's a sampling theorem. So the camera works very differently. The modulation of the camera works differently from the modulation of the laser beam, where you modulate the current of the laser. The laser, of course, is modulated, but the camera has to play along with it. So the camera has frames. So the camera can open and close a frame. From the sampling theorem, what you know is that I should be able to reproduce a sine waveform if I can have at least 2 measurements over one period. But you can do oversampling. You can have 4 measurements, 6 measurements, 8 measurements. So you can do oversampling of the waveform. The oversampling is the camera opens and closes and takes an image about a certain fraction of the period. So maybe at time t equals 0, at phase equals 0, at 90 degrees, or t over 4, at 100 degrees, t over 2, 3t over 4. So it opens up 4 times over one period. And then, once you have that, then you can reconstruct an amplitude and a phase. You can reconstruct the wave. Once you reconstruct the wave, you construct the amplitude and the phase delay of the wave, the phase lag. So that's how you get an image. So essentially a camera is worth, if it is a 300 by 300 pixels, it is worth about 10,000 lock-in amplifiers working together at the same time, because it does the lock-in detection by producing an amplitude and a phase based on these sampling times. Of course, cameras, the faster the camera can get, the better the image. But nowadays, you can get cameras that could be modulated at mid-infrared cameras are difficult to modulate, but maybe 170, 200 hertz. But if you can open up at a 200 hertz rate, that means that you're sampling. If you're to sample 4 times, then the highest frequency you're going to get is 40 to 50 hertz. That's what you can get, which is probably okay for thermal fields. It's okay. So we do the same thing now. We have a pulse train here, so do sampling of the chirp. So we do the same, except that now, of course, it has a dynamic aspect, because, as I said, single frequency gives you the, maybe I didn't say that, but I should say it. Single frequency gives you an average value over a certain depth. The depth is the thermal diffusion length, the square root of alpha over pi f. But if you want to do depth selected measurements, then you have to have multi-frequencies, and these multi-frequencies are coming here. So I'm planning to do depth selective thermal wave imaging. That's why I'm preparing, doing this kind of of sampling. Yeah.
One question. Just one more to clarify what was asked already before. So you're doing a sweep through all different frequencies.
Right.
Which was the frequency range that you
So, depending on how deep you want to go and what the thermal properties of the material are. If the material is a thermal insulator, which means like the diffusivity is very low, then you want to have ultra low frequencies, because if you want to reach deep, the heat does not deep. But I say typically from 0.1, from 0.2 hertz maybe to 100 hertz to 1,000 hertz. If you're really looking at thin coatings on surfaces, then 1,000 hertz, look at 1,000 hertz is difficult. So then, one of the ways that we overcome this, and we're not really working in that range yet, is to use some heterodyne schemes, which means that you have 2 frequencies going together, F1 and F2. Let's say I have 1,000 hertz and 1,010 hertz together. I mix the 2 fields just like a beat. You generate the beat wave. So I have the 1,000 and then the 10 hertz, F1 minus F2. So the camera locks onto the 10 hertz, which is very comfortable with. And what it does, it takes the amplitude of the high frequency end and brings it down to the low frequencies. So at 10 hertz, you get information about 1,000 hertz. That's one of the ways of doing that. But typically, I'd say 30, 50 hertz, 60 hertz, you can do now. You can do undersampling. That's the other thing that you can do. Instead of having every cycle sampling twice or 4 times, you do one cycle, you skip another one. So your frequency is still low, but you're going from 0 phase to 90-degree phase, not over the next, over the same cycle, but you skip one to the next one. That's undersampling. You can, so the third cycle is going to be the 180 degrees and so on. That allows you to still keep the frequency low. But if you do too much of that, too much undersampling, then there is a jitter coming in later on. So the field starts becoming a bit fuzzy out there if you do too much undersampling. So there's only so much you can do.
When you're doing all this in parallel, Andreas,
Yeah.
how do you control the illumination function?
Oh, there is, so you can...
Is it a broad illumination?
Broad illumination on the surface. You can homogenize the beam. We use diffusers, homogenize the beam. Or if you want to do local illumination, but of course then it defeats the purpose.
That's what I thought, that's what I was asking. So you,
So
when you
you
go
do-
to the camera approach, you change
That's
the
right.
illumination function.
That's right, yeah.
Yeah.
So these are some of the results that we see. We tried this on automotive gear. So there are cracks. That's what the industry wants you to be able to identify the cracks. So this was the case, 100 hertz lock-in. By the way, if you have a single frequency infrared measurement, that's a technique known as lock-in thermography. So everybody who is non-destructive testing field knows lock-in thermography. Started about 20-25 years ago. Gerd Busse in Germany started it at the time when people like me and others were working in thermal wave fields, and then that was developed at the time, so it is a well-known method. This is your crack right now, and the crack, of course, has disturbed the thermal wave field because it is an impedance. It does not allow the heat to go where it wants to go, so you see a different amplitude and phase. Typically, you see a higher amplitude at the edges of the crack because heat accumulates and it gives you higher temperature. And then this is what you see, the single lock-in. This is what you see now with the thermal wave radar. So it starts becoming a lot more, easier to see. The dynamic range is higher. You see that again, 100 hertz depth integrated lock-in thermography image, and this is a thermal wave radar image between 5 and 100 hertz. So here I see this, the crack being a lot more present. So that works very nicely for non-destructive testing. So we can understand, and also, of course, if you do depth profilometry, if you so cared, which most of the industry does not care, you can do depth profiling of the crack. So just by changing the frequency spectrum, how deep does the crack go? Yeah.
What's your main noise problem for these images?
I think this is the noise that comes in from the MCT. This could be a shot noise, but a lot of times it is the MCT. Well, the camera itself. So for the camera itself, the signal, the problem with the signals are coming in at low frequencies. You end up having 1/f. So that is because you work in low frequencies, you want to go in depth, and 1/f is the one that is giving you the majority of the noise.
What about background noise from the IR cameras, for example?
Because you're dynamic, what happens is the camera itself, the noise level, because it's cross-correlated, it just goes down to the baseline. You don't have much of a background noise itself. I mean, yes, there is thermal noise in the camera. That is always there. But don't forget that these cameras are cooled internally too. So these MCT detectors work, they're phononic detectors. That is, the phonon spectrum has to be really low in order to be able to produce a signal. So high temperatures, there's large numbers of phonons, and the camera goes haywire. It just doesn't give you much information. We use that for our single-ended dental diagnostic. We don't take the camera down to low temperatures, but the signals are so strong that I don't have to. I still see a signal in there. But most of the time, I think, yeah, this is the thermal component of the camera.
So can you remind ourselves what is the wavelength of the laser and what is the sensitivity?
Oh,
Spectral
for this
sensitivity
particular sample, it doesn't matter because the laser, it's a heating source. So in this case, we're using Jode lasers. These are from Germany, Genoptic, from Jena. Typically, I can go up to 20 to 30 watts. 40 watt peak power, I can have more if I want, but then the modulation frequency is relatively low, so there's no problem with that.
And the camera, the spectral sensitivity peak is where?
The camera is in the 2 to 3.5 microns. Now these are all the cameras that are actually controlled by external waveform. The active cameras are that way. You can have a passive camera in the 5 to 7 to 8 micron range. So the long wave range as well is available, but the imaging is not as good because the coherence, I mean, the camera has to open when the waveform gets to a certain point. Whereas in this case, the camera knows when the wave gets out because you put the wave into the camera. So it is driven by the wave. That's why it's expensive. That's why it's a $60,000 camera as opposed to the $6,000 camera. So we started looking at tooth and bone because there are optically turbid media, and again, in those tissues, the acoustic wave is hard, is scattering, but also importantly, it's not easy to put an acoustic detector on the tooth. A lot of these issues go back to the contact. You have to have a contact. The minute there is a contact, there's somebody at the University of Windsor in Ontario who is actually producing a dental diagnostic based on ultrasonics. I think that's a problem because a lot of times, depending on the pressure that you're putting on the sample, the signal changes. There are lots of people who try to do acoustics on this, but it does not work very well because the contact, your definition of how much pressure you put on the contact is different from his definition, so sometimes the signals change. Yeah.
What if you optically detect the acoustic wave?
To do acousto-optics.
The acoustic wave is a vibration.
Well, but you're generating light, right? You're generating light. You're using light, and you're generating heat and sound. The heat is very easy to pick up.
Okay.
So,
I think he's suggesting laser ultrasound,
Yeah.
which is interesting.
Laser ultrasound, yeah, you can do that, but I'm not sure that in this particular case, we're going to use that, because again, when you have the detector, the transducer has to be in contact.
No, that's what I'm saying. If you laser ultrasound,
Interferometric measurement.
Using-
Oh, yes, but your average dentist is not going to use that,
Yeah, maybe.
right? The average dentist wants to have a handpiece that looks like an Explorer, and then, so the Explorer has a hook. It goes in there, and so it looks at the occlusal part of the tooth, and looks at the interproximal part of the tooth. That's what you want. Once you start doing interferometry and things like that, it's not going to be a good match.
And
So-
what about the pole beard type
What?
set? What about the pole beard type setup? That's another type of optical pickup, isn't
yeah,
it?
but that needs contact.
Yeah,
Okay, you still need
That needs contact, but there's methods that don't need contact.
yeah.
That's a good insight over there, is maybe laser ultrasound, non-contact laser ultrasound.
Non-contact with air coupled transducer, that might be.
Sounds like a business opportunity to me with the clever design of a tool. Wink, wink, nod, nod.
Well, yeah, you can use interferometry, yeah, but convince the average dentist that they're going to use interferometry, especially because we wanted to use we're using 2 hertz modulation frequency here, and the idea was to use multi-frequency, maybe to stay on the tooth for about 3 or 4 seconds, and go 1 second per tooth and then go out, everything else, I lose money. So that's really what you're really facing for that. Because you have a true clinical system. And these are the components that make this about the only solution there is. So if you look at, again, you have a coupled, in this case, with teeth and bone, you have a couple of diffuse photon density and thermal wave field. So you have 2 diffusion equations. One of them is the optical diffusion, the one that was presented to you yesterday by David Voice, and let's say the diffusive limit, which means it is not really now at the ballistic limit. The ballistic limit 50 microns, so it's beyond that. So it's a diffusive limit. So in the diffusive limit, this equation is valid, and you have a field that is coherent and diffuse, and then you have the thermal field. So once I generate the optical field in the tooth glows, or the medium glows, or the bone glows, then I have this as the source of my thermal wave field. So then that sigma comes in. That sigma is the thermal wave vector, or wave number, so it has equal real and imaginary parts. The imaginary part is giving you information about the decay rate into the medium, but these 2 are diffusion equations. And the signal is an integral. This is the infrared radiation coefficient of the emission. So what happens is, at equilibrium, you have the Kirchhoff law that basically says that at equilibrium, the amount of thermal energy going in is equal to the amount of thermal energy going out, or even better, the radiation that comes in is equal to the radiation going out of the sample. That's the only way you can have equilibrium. Otherwise, if I don't have that, I can leave a sample out there in the air, and it's going to cool itself down just arbitrarily or heat itself up. Whereas we know that it's not going to happen. So at temperatures, at a given surroundings temperature, the amount of radiation going in is equal to the amount of radiation going out, so that the temperature remains fixed. There is no net gain or loss of thermal energy in the sample. So as a result, this is the infrared absorption or emission coefficient. And then I have an exponential decay, because the reason for that being that even though the infrared presents a problem, and the problem is that in most human tissues or animal tissues or live tissues, the great majority is made out of water. And water is extremely opaque in the infrared. Remember I was talking about before, when I said that that's what the predator is doing. The predator cannot see opaque things, but water is one of them. So especially at 2 or 3 microns, the peak of the water is really high. And again, about 10 microns, there's also a peak of the water spectrum. So it is important because that gives you information about the penetration. So optical penetration is not so easy. You know, have a very little optical penetration. But mind you, what generates a signal is a visible laser beam, a visible beam. So then you get the penetration that you want. The question is, once the light has penetrated, how much of that is coming out? So some of that is going to come out. In terms of teeth, the infrared spectrum has some windows. So some photons come out. And these are the photons that are going to come out of this. But there's also an exponential decay, that is a photon reabsorption as you're going through the medium. So those that are coming out are going to be a smaller number compared to those that started in. So that integral gives you that kind of information. So when we looked at teeth, the gold standard for teeth was transverse microradiography. This is an X-ray technique again. So you cut the tooth and you look at the part that's dark. So the part that's dark is due to caries. Dental caries is a demineralization of the tooth. So when you drink Coke or orange juice, your teeth demineralize. But overnight, they also remineralize again. And that remineralization process keeps us going with our teeth throughout the rest of our lives, because mostly if you didn't have that, and by the age of 6 or 7, nobody have had any teeth to speak of, because everything had been demineralized. So there's compact layers forming on the enamel due to the remineralization. But when you demineralize, then you lose mass, and the loss of mass is slightly below the surface. You have this wall here. That wall is very important because it protects you from further demineralization. So you can have teeth for the rest of your life. Otherwise you wouldn't. They will be dissolved. So, and then there is a dip here. This is where the caries is. This is where you have dissolved the teeth. So you have certain absorption and scattering coefficients involved. And eventually, if you're not careful, that caries goes into the dentin and eventually into the pulp. So this is the outcome. I'm not going to go into this. We spent lots of years in preparing this technology, but eventually I'm just going to show you these images that come out. And this was a tooth that had been demineralized, so you can get demineralization solutions for 2 days and 4 days. So this is the lock-in imaging down here. So you do lock-in at 0.01 hertz. And this is essentially the range you want to be if you want to see deep into the enamel and into the dentin. But you don't really see anything here. However, the lock-in phase at 1 hertz shows something here. Obviously, what you expect is that this is going to be demineralized less than that. But then when it comes to the thermal wave radar, you see we use a frequency range pretty similar to that, 0.01 hertz to 1 hertz every 6 seconds. This is 1 millimeter, and already the amplitude, the cross correlation shows the difference. The delay time, and especially the phase, are exactly where you want to be, because now you see the difference between the two. There's the less demineralization, more demineralization, the same thing here. And the good enamel is in between. And actually that has been the validation of that was done using this mineral content, which is with the transverse microradiography. So you just make little slices of that, and eventually you look at every slice of the tooth, and you find out that the number 1 is the one that has been demineralized little, number 3 has been demineralized more, and number 2 has not been demineralized at all. So you see the differences when you pick up an image.
So up to what depths can you detect demineralization?
I think that we're really looking, I'd say probably 500 microns, 1 millimeter, but then depending on what wavelength you use, that's very important, because the near infrared wavelengths, especially by above 900 nanometers, it becomes more and more transparent. So if you go to about 13 or 1400 nanometers, you start getting down to the dentin. You can be essentially transparent, but you say, why don't I use that? Because then you lose resolution, then you lose contrast. You don't see the Carey's effect. All you see is the big features. That is, you have the enamel and then you have the dentin. So it's a happy medium in between 800 to 900 to 1000 nanometers at most. I think that's what I would use in order to see these features. Otherwise, it just be washed out.
Viscosity, I think we can reach half millimeter.
Yeah, yes. Because also that's why the frequencies are so low. So this was the first part that you saw. Now we have something, but I didn't say anything about thermal coherence tomography. So what I have done so far, remember, even though we're doing this, we're still looking at a certain range of the peak, and that peak is relatively broad because it's a thermal wave. So the half width is quite broad. That means the actual resolution is not very good. You saw something, it's impressive, a dentist can use it, but if you really want to see, make it to the three-dimensional effect, then you're going to have a problem. So the next one that we did was, how do I improve the resolution? How do I improve essentially the actual resolution? But in order to improve the actual resolution, you have to beat diffusion. So this is really the key element here. That's why I started going into things like a binary phase code again that seems to be working better than the thermal wave, than the single sine scan. So it suppresses some of the side lobes and optimizes actual resolution. So what this really says, what it amounts to is to have a carrier wave. This was a 5 hertz carrier wave, and then there was a 7-bit code going into that. So at some point there's a flip over. So this is what these codes are doing. Sometimes they flip the waveform. So this is the time domain. You look at the Fourier transform of that, and you take this is a multiplication in the time domain. That's going to be essentially a convolution in the frequency domain. So as a result of the convolution, you see these two peaks. But the important thing is, because you have put the binary phase code, the peaks are really sharp. You see the bottom is broad, but the peak is sort of really sharp. So that allows more localization of the signal, more so than the single sine wave when you do a cross correlation of that. And these are some of the expressions for the Fourier transforms of the E, that's the Fourier transform of this bit code, and the Fourier transform of the entire thing. So you can see omega minus omega 0 is the repetition frequency too. So the repetition frequency is very important because the repetition frequency is the one that sets the thermal diffusion length. After all, it's still a thermal wave. So that means that how slow or how fast I repeat the waveform, that sets how deep I'm going to be able to see. If I repeat the waveform too fast, I'm going to see shallow. If I repeat the waveform too slow, I'm going to see deep, but I'm going to lose essentially the resolution, the spatial resolution and the actual resolution as well. So again, you have to use caution. This signal is a thermophotonic signal, that is, it is heat and there is photons coming out. So even though it is photothermal, but in this, the heat is generated by photon. However, it's thermophotonic in this case because the heat is generating photons of its own. So that's why I prefer to call it thermophotonic. And then we have theoretical expressions for that. I have the average of the infrared absorption coefficient, because remember, it's not a single, it's a spectrum. But more or less, it's okay to assume a mean value for the infrared absorption coefficient. So mu IR bar there. And you have two sources of signal, conduction and direct Planck radiation. So what happens is, this is the conduction term, the direct radiation term. Both of them are superposed on each other. Just to give you an idea, what I'm really expecting is this. If the material is transparent, is infrared transparent, then what will happen is, immediately I'm going to get those photons out from the from the depth. So that means that essentially there's very little phase because the photons are instantaneous. So I'm going to be getting amplitude that depends on radiative heat transfer, but I'm not going to be getting the phase that I want. Phase is important because the phase is independent of the intensity. once again. However, if the infrared medium is a bit opaque to the infrared photons, so many of them are going to be attenuated, then that gives a chance to the conduction heat transfer that is generated somewhere in here to propagate itself to the surface and therefore raise the temperature of the surface and be seen by the detector. So then I have a phase information. So it is nice not to be transparent in the infrared if you want to monitor phase. So that's exactly what we're sort of showing here. We have different codes at different frequencies, 1, 2, 5, 10, and 20 hertz for the carrier frequency that takes the code in. And then you can see that for 1 hertz, 200 inverse millimeters, this is a relatively high absorption coefficient. So you see I'm getting deep information of the phase from deep inside the sample. Whereas if I have a low absorption coefficient, I don't get much of a chance because the radiation heat transfer is the one that's coming out and it is dominating the signal. So I have a chance to see much more shallow than I see with the high absorption coefficient. So again, some like a bone or a tooth is just right because there are some optical windows, but all in all, there is an opaque medium there. So conduction heat transfer has a chance to come out and give me the image that I want. And if you compare between the FM versus PM, so FM is the frequency modulator, that is for the single sine wave frequency scan as opposed to the bit code, 16-bit code here, you can see how much better in terms of localization you are. This is the cross correlation for one versus the other. So you can see for a 50 micron thickness as opposed to 1 millimeter thickness, these are huge differences, but in both cases we basically have that the code generated signal has a higher spatial localization than the sine wave, which is exactly what you want if you're to somehow beat the diffuse part so that you can increase your axial resolution, which is the problem. So here it is, phase modulation uses better axial resolution than SNR as opposed to a single amplitude. And then you can see that as well. You see the PTR, if you did a single frequency measurement, that's your phase shift. If you did, on the other hand, a linear frequency scan, you get a much better resolution, frequency modulation here, and a much better resolution if you use a phase modulation, which is just introducing the code. So these are this is the outcome of that. Now we tried this. Remember I showed you before this diagram and how just single frequency would behave as I go deeper and deeper into the medium when the absorber moves farther and farther away from the surface. So I have washed out effects here. But then if you look at the cross correlation of the peak delay for the phase modulation, which is using the code, then it retains for each and every depth, it retains a resolution. The same thing for the delay time and for the phase. Unfortunately, I don't think that this image works. I tried it many times, but I was going to show, oh, wow, what do you know? So here goes. Surprise. So each and every location, now it shows very clearly that location as you're moving deep into the sample without the washout effect of diffusion, because again, you're having a much narrow autocorrelation. That's what it comes down to when you saw that cross-correlation function. The autocorrelation also of the thermal field is not much better. So anyway, let me show it once again, because at the time we're also very much impressed by the localization of the heat at different depths, all the way down to the deepest point. Okay, so the other thing that we tried with this one here was with holes. Remember, have holes at different depths. So we looked at the conventional 2 Hz lock-in thermography, and then we look at the binary phase code images at 2 Hz using 16-bit code. You see only 2 of the holes. Here you see essentially all 4 of the holes, including the deepest one. And here was the other one that basically made it into a thermal coherence tomography, or photothermal coherence tomography, which is now I have 2 absorbers, one of them at this depth, the other one at a different depth, making a cross. And then what we do this becomes essentially zeroing the time at each one of the two depths. So I can zero the time at 1, I can zero the time at 2, and then I use that. This is my microsonic interferometer now, right? Because I have a reference. So it says that the time t equals 0 is there. So heat moves from there on, and I can actually, depending on which time tau equals 0 I use, I can see the upper, this is the deeper absorber with little interference from the shallower absorber, or I can see the shallower absorber with little interference. Well, it doesn't look like little, but if I go to the next image, it looks much better. So this image, if I plot it a different way, it shows the tau 2, which is the deep absorber, with little interference of the upper absorber, and the tau 1, which is the shallower absorber with little interference of the other one. So why is this a coherence tomography again? Because it just goes in and sets the 0 time, and by setting the 0 time, you're actually looking at at where the peak of the response is going to be, and that response is narrow enough so it allows you to decouple layers one on top of the other. So now I can do imaging at different depths, and this is what optical coherence tomography does. It is a tomography in the depth sense, not in the scanning sense, that you start seeing different layers, different planes below the surface. So this is what I'm really targeting this for. And this was, again, we started looking at the interproximal
but
region.
Here you have no interference. Is in the,
You have no
is in the
interference.
procedure, yeah.
The interference is the instant wave meets the thermal wave, and it has a peak at that position because that's where your response is. So you can move that delay time to pick up other absorbers above and below, so you don't have that integrated effect. So it's depth resolved as opposed to depth integrated, which is really the major issue here, because it's a diffusive field you're talking about. So normally it wants to be depth integrated. So in this case, we start seeing the carries in between the interproximal area and and I have a little movie here that shows how it starts progressing. We have demineralized that region, so you start seeing at early times a defect here on the surface of the tooth, and then suddenly the caries appears in between. That's what's generated as part of the signal. So finally you can get other absorptions and you're done. But you really want to home in to see that signal from the caries, how that is generated. Because bacteria basically get in between the teeth and they stay there, and eventually they shed their proteins into the enamel, and that's how you start the rot of the tooth. So the enamel now decays, and the interesting thing is this method is also could be called an amplification method, because it amplifies. You have the thermal component amplifying the optical component, because the optical absorption coefficient changes. The crystalline structure, teeth are made of a material called hydroxyapatite. Hydroxyapatite has a definite crystalline structure. Locally, the crystalline structure changes. The absorption properties change, the optical properties, but also the thermal properties change, the conductivity and the diffusivity changes. The two of them work synergistically, one on top of the other, to give you a very early, a measure of very early detection of caries in between the teeth, or also in the occlusal area on top. So these are very hard to reach because the dentist cannot really reach very much in there, but something like this should be able to see what is the extent of your caries, and then if you catch them early on, you don't have to drill the tooth and fill it. You can just simply put ointments on that. If it's early on, you can put certain ointments that diffuse into the enamel and then restore the crystallinity of the enamel. So the dentist is going to be losing money because they're not going to be drilling the tooth, and the dentists really love patients that have bad teeth, because otherwise they'll be out of business. So they want your teeth to be bad because they want to fix your teeth. But on the other hand, if you give them this kind of a situation, this kind of solution, they can actually pass it on to their assistant. Somebody who can actually do the remineralization process, and because there's no x-ray here, they can call the patient every month or so to monitor the degree of remineralization, because it just takes more images every month. And every time you go, you pay. And if you can get a code, then the code is actually there, and your insurance is going to pay. So this is where we're at right now. So finally, I'm just going to say, to finish this part up, we have we look at the effect of surface. We look at bone. Bone is just as bad or just as good as tooth. Bone has a hard part on top that's called a cortical bone, and then there is a spongy part that's called trabecular. And then when you have things like osteoporosis, then that's going to start below the surface. So it starts, unfortunately, on the trabecular part, which is inside, but you have some changes in the density of the cortical part as well. But they're a lot smaller than the changes of the trabecular part. So you want to be able to see, can I use this method to see inside the, behind the wall? And you can see here, roughly speaking, I have the surface at a low frequency, and then I have a high frequency, I have a low frequency. High frequency sees the surface layer, low frequency sees below, but it's not good enough. I mean, this just got us started to thinking about this.
Excuse me, one question.
Yeah.
Comparison of this method with conventional X-ray. So you cannot see the progress of the like the cavities in the normal.
X-ray has very low contrast.
Okay.
So X-ray is also an X-ray. It's bad for you, bad for your children. So you don't have your children exposed to the X-ray, but it's very bad contrast. So X-ray is you're always going to be competing with X-rays, but nonetheless, the contrast here is great. So that's what makes this a winner. Let me say that with these methods, we get better axial depth resolution, we resolve overline absorbers, and we have depth selective thermal coherence tomography. I said, just set the time, tau 1, tau 2, that's your microscope interferometer now. So you're looking down, you're looking deep, you're looking shallow, but nonetheless, what I'm saying here is the last part of my presentation, which is the third part, that is we have been increasing this technology time after time after time. So first of all, we did the thermal wave radar, then we did the code, the binary code, but now we still need to do better, because this binary code, the thermal coherence tomography, because you can really sit at one depth and then go one depth after another by readjusting the time tau equals 0. The spectrum, the frequency spectrum, is not narrow enough to exclude weighted amplitude contributions from other depths. Heat is coming from other depths as well. So you want to be narrow enough to get the heat that's trapped only within a certain depth, but not from other depths, because that is going to introduce interferences. So there's a shadow effect there. Now, the time for the vertical 3D slice-by-slice image reconstruction can be long, because you have to move the time tau. So there's little room for further axial resolution, because binary codes are not known. That's the same effect we had with photoacoustics. So we tried this with photoacoustics, but we could not devise too many of these codes. So you have to have long codes in order to get narrower half width. Well, those codes are not known. So those features prevent this methodology for becoming a 3D imaging methodology that we want it to be with high resolution. So what is the answer to that? Our answer is truncated correlation for the thermal coherence tomography. So what this gives you is it basically localizes the heat at a particular depth, because you open up time windows in your cross correlation. So it gives you crisp imaging, breaking through the diffusion resolution of the depth barriers. Now this is really what you see in terms of, if you look at classical diffusion, you have two absorbers here. These absorbers eventually, as the heat propagates and merge, that's your Rayleigh limit here, where the thermal Rayleigh limit, where how far do they have to be before you can see the two of them separately. This was work that was done by Favre, Kuh, and Thomas. These are some of the first people working in the photothermal field in the 1980s and 90s, and these people were high energy inverse problem people, who started solving the inverse thermal wave problem to deconvolute from this to go there. But still a very poor resolution. So nothing much had been done since those days, actually. So this is a field that had been ripe for evolution. So we sort of introduced this, the TC, which is a thermal coherence, a truncated correlation for the thermal coherence tomography. So this field exhibits the highest degree of energy localization in a parabolic diffusion wave. I say parabolic, just the mathematics. This first order in time, that's what makes a parabolic field. That's diffusive. So what do we do here? We introduce a time-evolving filter controlled by pulse delay and truncation. So that gives you localization of the heat. You're only looking at one particular location, not above or below. And I have an excitation optical source, and I take a truncated cross-correlation process. Normally, when you think about cross-correlation, you don't think truncated. The intervals are from -infinity to +infinity. Here, we truncate it in time. So we can look at the spectrum within the instantaneous time window. So typically, what you do is you have a laser beam homogenizer here, so you're irradiating the whole surface homogeneously. This is a bone, there's an infrared camera here, and it picks up the information, and then it does something with it. So what does it do? It basically has an excitation chirp. It's a square converter. It is important to do that because you have to be able to get the out of phase. The out of phase in this situation cannot be given by Hilbert transform, as I said before. It has to be done with an XOR kind of this is a logical XOR. You have to take the double sweep, the double frequency, and then convert that into the quadrature using an XOR command, and I won't really go into that now, but we know we tried this. This is the one that works. So we do the time sweep, have an in-phase reference, and have a quadrature reference. This gives you the reference for the quadrature. Otherwise, you don't have a reference for that. That's why you need this. And then you do again a fast Fourier transform and a match filter. So it is a modified radar. And then eventually, when you get the mix in, you do an inverse Fourier transform of those frequency components, and you end up with a real and an imaginary part, or an amplitude and a phase. But this is how we do it in general. But then, what do you do? What does the match filter do? Well, here is a signal buried in the noise, ST, white noise. So you take the Fourier transform of that with the complex conjugate of the signal spectrum. This is your filter, and the output of the filter with the spectral response is given by this integral. And again, you end up with this is a Fourier transform of this. So it's a cross-correlation signal at t equals t0. So you can have different time evolutions or different cross-correlations at different times. Let me say, I did not say much about it yet, but all I'm saying is I'm showing you some of the first examples of this. We took the same block and we drilled holes in the back. We have H1, H2, H3, H4, H5, and we added some other holes that are deeper too. So we have 5 holes. This is 300 microns. So the front surface, back surface are the holes below there. With excitation chirp, from 0.2 to 0.6 hertz, duration 12 seconds, pulse widths 10 milliseconds, 30 and 60 milliseconds. Typical. So these are the results of the non-destructive imaging for truncated cross-correlation. I see the amplitude now. So the amplitudes, unfortunately, the amplitudes also depend on the optical properties of the surface because there's a reflectivity there. So the reflectivity of the surface, especially in a metal, so matters. Whatever stuff is on the surface, that's going to show up. The phase is better because it does not depend on the reflectivity. The phase is a ratio of two signals, quadrature divided by in phase. So as a result, the reflectivity cancels out. So that gives you that gives you a true thermal wave image. So you see now some of these holes. This is you barely see the 3 millimeter hole. Before what I showed you, I could not see the 3 millimeter, but now I barely see it. This is the peak delay time. Peak delay time and phase are related some ways, because the delay time gives me a phase, but they're not identical. The phase is not behaving as well as a peak delay time. And then there's the zero delay, when the phase dips through the zero, and that also has some information. But it looks like the peak delay time is the best for these. There are 4 images that I get out of this. But now I said, if you look in thermography, again the same thing, single frequency, 0.2 hertz, then we can see up to 1.5 millimeter beneath the steel surface. So amplitude, these are different holes here, so I can see the amplitude image of the phase image. Anything below 1.5 millimeters you can't see. Before I show you, it's down to 3 millimeters.
So before you apply the truncation of the correlation function, until this new title, the axial resolution was determined by the chirp, isn't it?
The axial resolution, this one here now, the chirp, this is a lock-in tomography, so it's depth average. But the chirp determines essentially the repetition time of the chirp determines how deep you're going to see. The repetition time of the chirp. The frequency content of the chirp also is going to determine your spatial resolution, because high frequencies delineate boundaries better. The actual resolution depends essentially on the decay time of the thermal profile. The thermal profile for each of these pulses, there's a thermal wave, right? And the thermal wave propagates. So the one that controls the actual resolution is on the lowest frequency, because that's the one that produces most of the diffusion.
So you improve the method with the truncation to achieve what? Axial resolution or acceleration?
I want to do both, but this one here is showing that I'm improving depth capability, so I can see deeper. I can see up to maybe 3 millimeters as opposed to 1.5 millimeters. But I also want to be able, but this is depth integrated here. That is, it knows that there's something below there because the heat propagates and then it starts sort of sitting at that interface and accumulating and giving me back a mean temperature. However, what I want to do is I want to be able to go in and look at individual slices below the surface to do 3D imaging. And that's where the optical coherence tomography, that's the tomography, so this is not tomographic. So what we did was we said, okay, let's look at some deeper subsurface imaging. So we created holes at 3.5 and 4 millimeters, and we used frequency sweeper. Of course, you have to adjust it. So now this became 0.08 hertz, because you have to be able to see deep, up to 0.6 hertz. So you have 27 seconds, so fairly long time in order to allow for the heat to go, but at least you should be able, you want to be able to see it. So the results for that is a very new results. We got those about a month and a half ago. My PhD student got this result. You have it. This is the amplitude, 3.5 and 4 millimeters. The amplitudes don't show very much because they're almost entirely controlled at that depth range by the reflectivity of the surface. So you see very little. But then the phase starts showing something. This is the location of the defect. The amplitude delay doesn't show very much. I think the phase delay, in this case, shows basically the feature. Now, these are the really deep, the 3.5 and the 4 millimeter depths. So this is really the state of the art in this thing. Now we can see 4 millimeters in a totally opaque sample from the surface. So we started looking at bones. So this is the TC-PCP of a goat femur. This is essentially, we took a goat bone and we drilled holes in it. So here is a hole coming from the back. Instead of having the steel square, the steel block, we have a bone. And then this is the narrow one. So we want to see how we can see that. So we set the parameters, and what this feature is doing, it is basically going in, as I said, instead of having the entire signal coming in over the total length of time, the integral, the correlation integral going from -infinity to plus infinity, we chopped the correlation integral for very short times. You cannot make a time t equals 0, because if the slice is t equals 0, then there's no energy there, so your signal goes down. So you have to have a certain width of the slice. The narrower the slice, when you do the cross correlation, the more heavily depth resolved your response is. Because you're picking up heat at that depth. There is no diffusion coming out. Whatever heat is there, you're picking it up at that depth. That's why now you can do depth profilometry. And this one here, I look at the amplitude and the phase. And then I look at, we can slice this over P1, a plane down that way, or a plane horizontally that way. Out of all those planes, I see the two holes. So here is the hole that was generated, radiating from the top. I see the hole generated by this drill. This is the fat drill, and this is the narrow drill right here. This is the back field. You remember there's a thermal field here. There's an interface. So heat tends to sit there, which means like now this is showing up as a heat accumulation. But this is the body of the drilled hole. This one shows the body of the fat drill. And what is interesting about this is that I also see something on top. What that something on top is, it's a thermal wave field that is generated above the surface of the drilled area. That is, there is a thermal wave field in the solid, and then there is a thermal wave field right up on top in the air that comes out here. So this is sensitive enough to see the thermal wave field in the air as well.
So how are the 25 micron and 2 millisecond connected? Shall I infer the velocity of the diffusive wave from these two?
Well, there is a diffusivity, that's right. So when you look at the pulse width was 2 milliseconds. So that means that what you're doing is you're really doing repetitive pulses. So you say, how much of a repetition time or delay time do I have to do to see discrete layers? At 25 microns, maybe I added 10 of them or 20 of them for 250 or 500 500 microns. So these are the depths, 500 microns, 1 millimeter, 200 microns, that's what you're really doing. So each one of them you delay by some. If you delay too much, then you start overlapping with the next. You see, each one of them, you're generating your pulse. It's a thermal pulse, so it's a thermal decay, so it's decaying. As it's decaying, you could overlap with the previous pulse, but you're putting your window right below the pulse here. So you delay your window to catch this decay time, this decay time, this decay time, and each one of them is localized because it picks up the heat within that time interval. That's what it's doing. So this turned out to be just right because of the thickness of the sample as well as the thermal profile. The thermal profile in bone is the diffusivity is low. That allows you essentially to keep yourself going into the medium for quite a certain amount of time, and then you can see a certain depth. But what I'd say, instead of looking at all these, I'm just basically looking, the amplitude seems to be the best. This AM, which is the amplitude, and the initial phase is also showing some features, definitely high resolution. The amplitude delay, yes, it has a high contrast. And the zero crossing of the phase is also indicative. You also see features like that, but the amplitude is really the best in terms of the imaging. So what this allows you to do is, again, to do delay time imaging. So I have this gold bone here, and I pick up early time. So time runs here in milliseconds. So we have looked at planar images, 10 millisecond reference delay intervals. Each one of them shows you different characteristics below the surface. So you pick up the cortical bone, and then eventually you pick up the trabecular bone. But of course, this is diffusion again, so you're not going to be picking up all of the details of the trabecular. You're going to be picking up something that will be commensurate with the thermal wavelength. You're going to see the general features of the trabecular bone, but you're not going to be able to see the individual holes. This will take you to high a frequency, which means that you won't be able to penetrate the cortical bone. However, this could be good enough because you can do statistics. You say, okay, for a healthy bone, for a healthy individual that is not suffering from osteoporosis, maybe this is the range of signals that we should see. And then as the density changes, then those things could change as well. So one can build up some of the statistics of that. We've seen this. Now let me show you what we've done with that. We took chicken breast and we put it on top of bone. So this is 0.6 millimeters thickness of chicken breast, and then I have 1.2 millimeters of the cortical bone, and then there is a trabecular bone below here. So this is what we're looking at. This range is flat range, and then we get the on C here, I get a binarized amplitude. Now, binarized amplitude, when you do imaging, this imaging is very good with its best seen if you start putting some degree of transparency in the medium. So you can add a degree of transparency that takes away part of the opacity, but also it shows you what happens below. If you make a 30% transparency or 40%, you see things below. You cannot put too much transparency because you start losing signals. But with a certain degree of transparency, I'll just say, you look at this one here. This part reconstructs basically the trabecular bone below. This part reconstructs the cortical bone on top, and this part is the chicken, the chicken breast on top. So you can see the interfaces very clearly. You start sort of moving deeper into the sample. You can look at it from the top. You can look at it from the bottom. This is what you get again in a case of demineralization of this gold rib. We can start demineralizing the bone. When you demineralize the bone, it starts fusing. Bones, neighboring regions start fusing. So here is the case where we looked at early on, intact, 0.5 hours and 20 hours of demineralization. So you, in the B1 to 3, binarized amplitude tomograph of the trabecular layer. So you can see the trabecular layer right here. You don't really see the individual honeycomb, but you see the general structure of the trabecular layer. And in fact, you can start seeing the demineralization early on. Half an hour later, some of these features start changing. Of course, 20 hours later, everything kind of fused together. So you can see that quite clearly. But this was a discontinuous surface because you look at it from the trabecular side. If you take the image from the other side, all these images are connected together. Then you see the more compact image of the cortical layer from the top. And then this is a cross-sectional image. And this is now the infrared image that you use in lock-in tomography. So they're just hints of what you see. This part is this part right here. This part down there is going to be there. You see those aspects, but it is a far cry what I see with lock-in thermography compared with the resolution that I have there. So in terms of actual resolution, mind you, now I have a microscope interferometer again, and that microscope interferometer is the time slice that moves further down and down and down, and every time, for every location of the slice, I cross-correlate the entire signal with that time delay slice. So I have the binarized amplitude in A and C, layer by layer. These layers were 10 sequences, 300 microns thick each. So you can see pretty deep, you can see millimeters now in there. So you can see for different depths how these things appear. And eventually, you can solve, this is why I said this is the equivalent of optical coherence tomography. It's a photothermal coherence tomography, because the tomography is now going, so depth resolved, and then I can see a three-dimensional, this is now putting them all together and getting a three-dimensional picture of what lies below the surface of that bone. So if I'm lucky, this may work. I'm lucky and it works. So you can see the amplitude image as you're rotating around, and you get some of the intricate information about the trabecular layer. This is the amplitude image, and you also have a phase image. And that also has additional information, maybe better information, because, so the trabecular part is really solid, so the cortical part is solid, and the trabecular is the one that shows the structure inside. I'll just run it once again. So this is where we are.
So Andreas, I think I have the same question that Adrian asked before. In order to make the identification of depth, to say this is 300 microns below a surface, you have to assume a certain...
Some properties.
Yeah, the diffusivity or the diffusion times or something like that.
Which you don't know.
How do you know it's right?
Which you don't know. But what you do is, you do repeat, again, you do these measurements and you try to optimize your signal. We know what the thermal diffusivity of bone is, because it's been measured, some thermal diffusivities. So the absorption coefficient is something that we don't really know, but what we do with this is we try to do time slicing over different frequency ranges. So for this one, if I take the sample, I choose some frequency ranges. Even based on that, I know I have to go from 0.1 hertz to maybe 2 hertz. So that range allows me at least to see something, and then I may start becoming a bit better. So I agree with you. It's not a quantitative; it's a qualitative image, but you know the range of frequencies that you're.
Yeah, so I mean, you know that you're picking out a slice which may be, 300 plus or minus 20 or 30.
That's right.
But you have an ambiguity of where that depth is. So I mean, if I go across the cross-section of the image, it may not actually be a slice, right? It may be something that's wandering.
Yeah, it's slices, different slices going all the way.
No,
so
this is a constant time. So if it's a constant time, if there's any change in the material characteristics as I go across, it's going to be a different depth, right?
Yeah, locally. So it is how the image appears. So it's chronotomy. It's chronotomography.
Yeah, it's constant time, right?
It's constant
time, but you don't know that that's constant in space.
No, you don't know it's constant in space, but you know that there's a defect there. So locally,
you know there's a defect. I get that.
Yeah,
but you may not know exactly where.
No, so it's a time tomography.
Yeah.
And this is, again, the other thing that we can do with this is we introduce this photothermal wave occupation index, which basically gives you this ratio of U over V, and U and V are the volumes of the active bone components and the cube element. You have a cube here, so the value of the signal that you get is related to the total amount of thermal wave signal that is generated within a certain volume, and that allows you to do things like this, to look at the fractional change in the bone mass density. We did that independently. This is the fractional change. So the before etching, we etch the bone before etching minus after etching divided by before etching times 100. So that gives you an idea of how the bone changes after a change in the density has occurred. So this, which is demineralization. So these fractional changes are basically showing how consistent it is with measurement, independent measurement, where we use this methodology here, a SkyScan 1173 Bruker, micro CT. Micro CT is an X-ray based methodology, so it can give you precise information about the density of the medium, and then you can see the increases here up to a certain point, but then this kind, whereas this one here continues on, this collapses because the whole structure of the bone collapses after a certain amount of demineralization, and that is showing that way. Obviously what is happening is the thermal wave before, because the thermal wave signal after decreases as the bone becomes a poorer, and has less and less meat in it, less and less bone, so it's mostly air because it demineralizes. So I get less and less of a signal because there's nothing to create a signal on. If there's nothing left, there's no signal. So as the density goes down, so does the signal. And therefore, the relative signal increases because it is the before minus the after. But then eventually here it tells you that this whole thing is decaying, it's collapsing. I'm not even sure if this is still valid, but if your bones come to the point where they have fused together, then you know that you're desperate. I mean, we're really looking at the early stages of the formation of things like osteoporosis. You're never going to have a human standing on his or her feet where the bones are going to be fused that much. I mean, you're going to lose 90% of your bone structure, so you're dead already before you get to that point. But what I'm saying is this may allow us to do some things. And then I'll leave this one, this is my final application here, which is looking at the burn depth analysis. So we took a pig's ear and made 2 burns of that. And here are the 2 burns, and we added a certain degree of transparency here. So let me go through this picture. A photograph of a pig's ear specimen with 2 burns. The red envelope is the imaged area, so you can see the red envelope here. Amplitude tomogram, as observed from the tissue surface. So here I have clearly shown the 2 burns. Amplitude tomogram with 60% transparency. So once you do the transparency, that means you're allowing some of the underlying structures to appear. And sure enough, you see now the holes that are left below the burn, because you put a wire there and you started burning the whole thing. So locally, you have changes in the structure, not only on the surface, but below the surface as well. And so this D is amplitude tomogram with transparency and threshold optimized for burn depth profile inspection. The needle-like structures at the bottom XY, so you can see these ones here, are due to follicles without hair, whose presence can be seen. These are the needle-like structures down here. But importantly, I see the images of the 2 burned cylinders showing up from below. And what you see with the photography, of course, the photography in part E shows of the burned cross-section. The red scale is 5 millimeters here. So the photography doesn't show much of that resolution the way we see it with the tomography. And then when you go to another case here, F is a photograph of the second sample with a different burn. This was a more severe burn, but it shows a bit more clearly here. You see different stages of the burn. This equivalent, once you have the transparency, you see the depth and the extent of the burn down here. And of course, you get a lot more information here than you get from the cross-sectional image. So compare that with pulse photoacoustic imaging, and we send that to the University of Michigan, Zinwei 1.
Shooting one.
Right. Zhuoding. And we did imaging at 50 megahertz. This is a photoacoustic image obtained at 50 megahertz of the sample. And then we have the same coordinate system. We don't see very much with that. That's because also both the optical and the acoustic field are scattering. Even the interface is not involved as much. We put together a preliminary table. That table is subject to change, but this was like the first of the results that we got. The quantitative comparison of properties of 3 non-ionized and non-invasive techniques for bone diagnostics. Technique depth range, so for acoustics at 3 megahertz, Depth range, we get about 3 millimeters in bone. Very little depth range. It does not penetrate very deep. Lateral resolution, 1,000 microns. Axial resolution, 1,000 microns. Signal to baseline ratio, 4 to 6. The demineralization sensitivity, high on the cortical, low on the trabecular. It does not penetrate. And we see that typical speed in terms of seconds, 10 seconds. These are the studies that we did at the University of Michigan. And then for acoustics at 20 megahertz is better. Of course, the depth range, of course, is much shorter, 1.3 millimeters. But we get better axial resolution, and some of the other parameters are more or less a guess. Optical coherence tomography, now these are things that we got from the literature. Depth range, less about 1 millimeter. Lateral resolution, very high, 10 to 15 in practice microns. Axial resolution, very high. The demineralization sensitivity, moderate, comes in from references. This photothermal coherence tomography sees about 3.2 millimeters or better, maybe 4 millimeters. Lateral resolution, nowhere as good as the OCT, but 100 maybe can get better than 100 microns. 25 for axial resolution. So there is, but the important thing is also signal to baseline ratio, very high. So you know that it has future to give you some good results. So conclusions. We basically ended up with a match filtering in diffusion wave fields that gave us a localization. We did 3 methodologies to optimize the localization. One of them was chirped, the thermal wave radar, binary phase code, and truncated correlation photothermal coherence tomography. Energy localization for the chirp, but not very good. The binary method better, but it's not optimally narrowband to do 3-dimensional tomography. Oops. And the third method, the truncated correlation, was the highest thermal wave localization resolution to date, about 4 millimeters, and that, being depth selective, gives you a thermal coherence tomography, the photothermal counterpart of optical coherence tomography. And I'm going to leave it at that. We're still doing more studies now with small animals like mice, like rats, and so on, to be able to do depth tomography of brains, rat brains. This is the next thing that we're working on, and I just wanted to acknowledge the funding agencies that everybody has to pay service to.
Thank you to Andreas for that extraordinary tour through photothermal. Do we have some questions? We're ready for the dinner.
So what do you identify as the bottleneck of the technology? Where? Is it the camera? Is it the controller?
Cameras are great.
Localization of the
cameras are getting better. I think it's still a challenging tomography. That is, you have to know what you're doing, and you have it's not automated yet. It's very early stage. So I think that I won't call the bottleneck, but I say where it wins. I think it wins in hard tissue. It's going to win in dental tissue. It's going to win in bones. It's going to win maybe in looking at the effect of osteoporosis, bone osteoporosis. I think the other thing is small animal imaging. I mean, just making a machine to image small animals. When you look at the iThera in photoacoustics, of course, it's much deeper penetration, but the point is you have to take the mouse, put it in the water inside the photoacoustic chamber, and have a little muzzle here to put oxygen on it. Well, we started working. Right now we had in vitro animals, but we're going to try to do some in vivo animals where you can actually have the mouse there alive and kicking and start to look at the brain of the mouse, for instance. Pretty much like what Leon Wang's group had done in 2003, 2004 for acoustics. The results that we're getting so far is we can start seeing the brain with the cap on, with the skull on. But you don't need the photoacoustic transducer rays, you do not need the water interface. So that to me sounds like the camera is basically ready to take your image right there.
And a comment now, you worked with Benamaetia.
I'm going to do what?
You worked with Benamaetia.
Yeah.
So I saw that paper.
Yeah, well.
So we did together one of the first demineralization in Britain. It was in Britain.
Well,
So you
dental.
have someone who already has done OCT, so
Well, yes, so
was he happy with the
we
results?
learn a lot from OCT because this is the photothermal equivalent of OCT. So we do need to get to people who know the OCT methodology. And OCT has been used, as you know, already in teeth. But again, it's not an easy method to use. So I think this one here, with OCT, dental OCT, you have all these reflections from inhomogeneities of teeth that give you a baseline that you cannot go below. This one here will not depend on the reflection because reflection is optical, this is thermal. So again, there are advantages. So I see, yeah, dental and bone, these are the two major issues right now that I see.
Okay, thank you for that. So you will have noticed that we have two poster sessions. So the professor is going to take it easy, and you guys are going to be in the chair for the next few hours. This is after dinner, of course. Don't worry, we didn't cancel the dinner yet. For the first session, we're going to have everybody up as far as Jamin Lee. That is all the letters before that, and